Welcome to Ordinary Differential Equations, Lesson 22, Determinants of Matrices. The goals of this lecture are to calculate the determinant of a square matrix using expansion by minors. Only square matrices have determinants that are defined. Use MATLAB or SageMath to calculate a determinant. We want to learn the properties of determinants, determine if a square matrix A is invertible or not by considering its determinant, determine if the equation AX equals B has exactly one solution or an infinite number of solutions, or perhaps no solution, and also apply Cramer's rule to find the value of one or more variables in the solution of n linear algebraic equations in n unknowns. So let's talk about the determinant of a 2 by 2 matrix, 2 rows, 2 columns. First, notations that we will use for the determinant of A are det of A, determinant of A, and also this represents the determinant of A. Looks like absolute value of A, but it's determinant when A is a matrix. The determinant of a 2 by 2 matrix, 2 rows, 2 columns, is defined the following. The determinant of this matrix is A times D minus B times C. The product of the elements on the main diagonal minus the product of the elements on this secondary diagonal. For example, suppose we look at the determinant of this matrix. It's going to be minus 2 times 3 minus 1 times 4. That's what we have here. Minus 6 minus 4 equals minus 10. Notice that the determinant of a matrix is a number. It could be positive, negative, or 0. What about 3 by 3 matrices, 4 by 4, and so on? Determinants are defined for all square matrices. A square matrix has the same number of rows as columns. Well, it turns out that it's more complicated, I guess you can say, to calculate determinants of larger size square matrices. It's just not the difference of the product of diagonals as we had here. We will see that later. Let's talk about the relationship between the determinant of a matrix and whether or not it has an inverse. We are still just talking about 2 by 2 matrices, but what we're about to say does hold for larger square matrices also. First fact, for a 2 by 2 matrix, these statements are equivalent. First statement, A is invertible. Second statement, the determinant of A is not 0. And the third statement, the equation AX equals B has a unique solution for any B in R2. B being a vector with 2 components. And in fact, that unique solution is X equals A inverse B. Another fact, if the determinant of A is equal to 0, then, first of all, A is not invertible. And secondly, if you look at the equation AX equals B, this equation has either no solution or an infinite number of solutions. Whether it has no solution or an infinite number of solutions depends on what B is over here. Let's look at 3 examples illustrating the 2 facts that we just looked at. Let's consider this system of linear equations. Minus 2x plus y equals 6, 4x plus 3y equals 14. Here is the augmented matrix for this system of equations, and if we look at the reduced row echelon form of this matrix, it turns out to be this matrix. And this matrix says that 1 times x equals minus 0.4. This equation says 1 times y equals 5.2. So x is minus 0.4, y has to be 5.2. There's exactly one solution. The determinant of this 2 by 2 matrix is easy to compute. Minus 6 minus 4, that's minus 10, which is not 0. Also, it turns out that this matrix is invertible. If we use one of our methods for finding inverses, we'll find that the inverse of this matrix is this matrix. Let's move on to another example. Let's consider this system of linear equations. It looks kind of similar to these, but a couple differences. Instead of a 3y, we have a 2y, and instead of a 14 here, we have 12. So let's consider these two equations. If you look at them carefully, and if you've had enough caffeine today, you'll notice that the second equation is just twice the first equation. Twice this stuff is minus 4x plus 2y. Twice the 6 is 12. So this second equation doesn't give us any extra restrictions on x and y. Whenever this first equation is satisfied, the second equation is also going to be automatically satisfied. So the solution set can actually just be found by this one equation up here. We could pick y to be any real number and figure out a value for x that would make this equation hold. So that would tell us that we have infinitely many solutions. If we didn't notice that, we could use our standard procedure. Here is the augmented matrix for the system of equations. The reduced row echelon form of this matrix is this one. Looking at this one, the variable x is a leading variable. The variable y is a free variable. And so we could let y be any number and substitute it into x minus a half y equals minus 3 and solve for x. That would also tell us that we have infinitely many solutions. This last line, all zeros, does not put any extra restrictions on x and y. The determinant of this matrix is, let's see, minus 4 minus a minus 4, which is 0. The determinant is 0. This matrix is not invertible. Another example, similar set of equations to what we have up here, but we just changed this 12 to a 33. Well, what does that do? Well, if we double this first equation, we would still have minus 4x plus 2y equals 12. And if that's true, how can minus 4x plus 2y equal 33? These two equations are inconsistent. So this system of linear equations has no solution, and just as we had up here, the determinant of this matrix is 0. So what we've seen is three separate systems of equations. If the determinant of the coefficient matrix is 0, we could either have infinitely many solutions or no solution. At least those are two possibilities. And over here, when the determinant was not 0, the system had one solution, and that turned out to be because the matrix was invertible. So this illustrates the two facts that we saw on the previous slide. So now we want to start the process of defining a way of computing determinants of larger matrices. You might ask, well, you're just going to give us a computational formula, but is there a way to think of determinants in an abstract form such that instead of just having a computational formula, you could actually say something about what a determinant is? And the answer, in a way, is that an actual definition of the determinant of an n by n matrix is beyond the scope of what we're going to do. But if you look in some linear algebra books, say for a second course in linear algebra, maybe a course a little bit higher than an elementary linear algebra course, you'll find that the determinant is an alternating multilinear functional of the columns of the matrix such that the determinant of the identity matrix is equal to 1. And from that definition, we could actually come up with the formulas that we're going to see. One book that you might like to look at for this sort of thing is Linear Algebra by Hoffman and Kuntz. It's a fairly old book now, but I think it's still in print and was very popular for decades for a first or second course in linear algebra, depending on what university you went to. So let's talk about the ijth submatrix of A. We're going to call that A sub ij, capital A sub ij. And we get A sub ij by deleting the ith row and the jth column of A. So if A is an n by n matrix, this submatrix is going to be n minus 1 by n minus 1. One less row, one less column, since you're deleting a row and you're deleting a column. So let's look at an example. Let's consider this 3 by 3 matrix. Okay, let's look at the submatrix A sub 1, 1. To get that, we're going to delete this row, 1, 2, 3, and we're going to delete this column, 1, 27, minus 1. We're deleting those because basically this is the 1, 1 element of the matrix A. So we're deleting the row that little a sub 1, 1 is in. We're deleting the column that little a sub 1, 1 is in. And so what we're going to be left with is this submatrix here, 0, 5, 6, 7. How about A sub 2, 3? In that case, we will delete the second row and the third column. And what we're left with is 1, 2, minus 1, 6. So A sub 2, 3 is 1, 2, minus 1, 6. If you think about it for a minute, we have 9 choices of I and J for a 3 by 3 matrix. So there are 9 different submatrices that we could talk about. Now, let's also define the ijth minor of A. Here we're defining a submatrix. Here we're defining a minor. M sub ij, the ijth minor, is just the determinant of the ijth submatrix. So this minor is a derivative, and so it's a number. So let's look at this same matrix we had up here, and let's find the 1, 1 minor of this matrix. So what do? Well, first of all, we have to see what capital A sub 1, 1 is, and we've already done that. It's this matrix, 0, 5, 6, 7. And so the minor, the 1, 1 minor, is the determinant of this matrix. So it's 0 times 7 minus 5 times 6, which is minus 30. M sub 2, 3, the 2, 3 minor of A, is the determinant of A sub 2, 3. So we're taking the determinant of this matrix, and that determinant is 1 times 6 minus 2 times minus 1. So that is 6 plus 2, and that is equal to 8. So what's going to happen next is we will use a formula, which we can refer to as expansion by minors, to calculate the determinant of these larger size square matrices. In a minute or two, we should be able to calculate the determinant of this 3 by 3 matrix. Actually, we'll be able to write down a formula for it. It'll take more than a minute or two to do the calculations, I suspect. Note that if A is an n by n square matrix, then one of those submatrices, let's say A sub ij for a given I and j, is going to be an n minus 1 by n minus 1 matrix. Aij is smaller than A. So for instance, if A is a 3 by 3, these submatrices are going to be 2 by 2s, and we already know how to compute the determinant of 2 by 2 matrices. We can find the determinant of a matrix by using what's called expansion by minors. Let's suppose that A is an n by n matrix. Choose one row or choose one column of A. Then do the following. For each element A sub ij in that row or column, create a term minus 1 to the I plus j times A sub ij times the determinant of A sub ij. Then the determinant of A is just equal to the sum of all of these terms for that row or column. This method of computing the determinant is called expansion by minors. Any row or column of A can be used for expansion by minors, and if a particular row or column has lots of zeros in it, your work might be a lot shorter to pick that row which has lots of zeros. Since the submatrices are n minus 1 by n minus 1, if you started, for instance, with a 3 by 3 matrix, then the submatrices here are 2 by 2s, and we know how to find the determinant of a 2 by 2. But suppose that A was a 4 by 4 matrix. In that case, the submatrices here would be 3 by 3s. And how do you compute the matrix of a 3 by 3 matrix? By using this method of expansion by minors. So, if necessary, expansion by minors can be used again and again to find the determinants of the submatrices that occur during your calculation. As an example of this expansion by minors, let's let A be this 3 by 3 matrix, and we'll find the determinant of A by expansion by minors along the first row. So we're going to use this highlighted row. So here's what happens. For this element 1 in this row, we're going to have minus 1 to the 1 plus 1 times that element 1 times the determinant of the matrix we get by crossing out the column and the row this one is in. And so the submatrix is right here, 0, 8, 2, 3. Okay? Then move on to 5. This is the 1, 2 entry. So we have, for that term, minus 1 to the 1 plus 2 times the 5 times the determinant of what submatrix? Delete this row and this column, and you're left with the submatrix 2, 8, 1, 3. Here it is, 2, 8, 1, 3. Move on to the last element in this first row. 2 is in the 1, 3 position, so we're going to have plus minus 1 to the 1 plus 3 times that element 2 times the determinant of the submatrix, which is given right here, 2, 0, 1, 2. And now, The rest is pretty easy. Minus 1 squared is 1 times 1. This determinant is 0 minus 16. Move on to this term. Minus 1 cubed is minus 1 times 5. And then this determinant is 6 minus 8. And then this last term, minus 1 to the fourth is 1 times 2 times this determinant, which is 4 minus 0. And so that explains this line of computation. And these terms turn out to be minus 16 plus 10 plus 8. Add those up and you get 2. The determinant of this matrix is 2. If we want to write down a formula for that determinant by expansion by minors along the first row, this is what it looks like. It uses the 1, 1 term, the 1, 2 term, all the way through the 1 a sub 1 sub n term if you're looking at an A, which is a matrix A, which is n by n. Just to reiterate some of the points we just talked about, let's look at one term from the expansion by minors. In general, it's going to look something like this. Minus 1 to the I plus j times little a sub ij times the determinant of the submatrix A sub ij. Okay, so let's look at this. This has three factors, this factor, and this factor right here. Minus 1 to the I plus j. This factor is either minus 1 or plus 1. Minus 1 to an odd power is minus 1. Minus 1 to an even power is plus 1. So what's going to happen is this sort of thing is going to make the terms in that expansion alternate. Minus plus or plus minus. Okay, little a sub ij is the ijth element of the matrix A, and the determinant of capital A sub ij is the determinant of the ijth submatrix of A. We called that, remember, the ijth minor of A. So sometimes you might see this term written as minus 1 to the I plus j times little a sub ij times m sub ij, the ijth minor. For an n by n matrix, you're going to have n terms similar to this in the expansion by minors formula. Let's see how we can find the determinant of that matrix using Sage Math and MATLAB. Here is some Sage Math code using a Jupyter notebook. The first thing we do is define the matrix A. A equals matrix. Then we have square brackets enclosing the rows. Each row itself is enclosed in square brackets. The elements in the rows are separated by commas. Two rows are also separated by commas. So A equals this matrix, and then we'll just display it, show A. So here's the matrix. To find the determinant, we just have A dot determinant, and then left and right parentheses. When we execute this command by using Shift-Enter, we get the output 2. The determinant of this matrix is 2. Here's similar code in MATLAB. We could say A equals, then 152, semicolon, 208, semicolon, 123. We have a row, then a semicolon, another row, semicolon, our third row. When we hit enter, it'll come back and tell us that A is this matrix. We could also put commas between the elements of a row. We could say here 1, 5, 2, 2, 0, 8, 1, 2, 3, and that will work also. To find the determinant of a matrix, we use the built-in function det. The determinant of A turns out to be 2.000. Let's find the determinant of this same matrix a different way. Let's expand by minors along the second column. So here's the same matrix. We're going to find the determinant by expanding along this second column. So let's see. The first, we're going to have three terms once again in our expansion. The first one is based on this element right here. This is the 1, 2 element. So we have minus 1 to the 1 plus 2 times this element, which is 5, times the determinant of the matrix that we get by deleting the row and column that's in. And so the submatrix is 2, 8, 1, 3. That's what we have right here. Okay, then we move down to here. And this is the 2, 2 element. So we're going to have minus 1 to the 2 plus 2 times this element, 0, times the determinant that we get by crossing out the row and the column of this 2 by 2, 2 element. So the submatrix we get is 1, 2, 1, 3, which we have right here. The next term corresponds to this location, which is the 2, 3 entry. So we have minus 1 to the 2 plus 3 times this element, which is 2, times the determinant of the matrix we get by crossing out the row and column that this element is in, and that leaves the submatrix 1, 2, 2, 8, which we have here. Now the rest of the calculation is very similar to what we did before. Minus 1 to an odd power is minus 1 times 5. This determinant is 6 minus 8. Move on to the next term. Minus 1 to an even power is 1 times 0 times this determinant. We calculated it here, but we really didn't need to because we're multiplying by 0. Plus minus 1 to an odd power, which is minus 1, times 2, which is here, times 8 minus 4, which we got from that submatrix determinant. And so this then equals 10 plus 0 minus 8, which once again is 2. So before we got this determinant of this matrix was 2. This time we still got that it's 2. We calculated this determinant of the same matrix twice. Once expansion by minors along the first row, and then here expansion by minors along the second column. We found that the determinant of A was 2 in both cases, both times. We could use any row, we could use any column for our expansion, and we'll still get the same number in the end, assuming that we do our calculations correctly. So it doesn't matter when you're expanding by minors what row nor what column you choose to use. Most people would choose to use a row or column, if possible, that has one or more zeros in it, because then the calculation becomes easier, because something times 0 times something is going to be 0. It doesn't require much thinking, at least for terms that have a 0 factor. So in any case, for this particular matrix, we could have picked this row, this row, this row, or this column, or this column. So there were 8 choices for evaluating the determinant of A using expansion by minors. So let's discuss some properties of determinants of square matrices, n by n rows, n columns. Suppose capital I sub n is the n by n identity matrix. Remember, that's the matrix with 1s on the main diagonal, 0s everywhere else. Then it turns out the determinant of the identity matrix is 1. So no matter what size matrix we look at, the determinant of the identity matrix is always 1. Another interesting fact, let's let A and B both be n by n matrices. Then the determinant of A times B is equal to the determinant of A times the determinant of B. Another property that we need to know is that an n by n matrix A is invertible if and only if its determinant is non-zero. A is, on the other hand, not invertible if and only if its determinant is zero. So, using this property that the determinant of A times B is the determinant of A times the determinant of B, we can easily see that the determinant of A inverse has to be 1 over the determinant of A. Why would that be true? Well, suppose we had the determinant of A times A inverse here. That would be the determinant of an identity matrix, which is 1. And so here we would have 1 equals the determinant of A times the determinant of A inverse, and then by division you would get this formula. Another property, if A is invertible in n by n matrix, in other words, if its determinant of A is not 0, then the equation AX equals B has exactly one solution. And by multiplying both sides of this equation on the left by A inverse, we can solve for X. X is equal to A inverse B. On the other hand, if A is not invertible, in that case we know the determinant of A has to be 0, then the equation AX equals B has either an infinite number of solutions or no solution at all, inconsistent equations. So far, everything that we have done in this lesson has been linear algebra. We're going to use this material later when we talk about differential equations. For ordinary differential equations, the crucial property that we're going to use is a relationship between the determinant and invertibility. And this concept of the relationship between those two is going to help us later to compute eigenvalues and eigenvectors of a matrix and help us to solve systems of linear ordinary differential equations. As an example, let's let A be this matrix, and for what values of lambda is the matrix A minus lambda I not invertible? So A minus lambda I is going to be this matrix with lambda subtracted from the main diagonal. Remember that I is the 3 by 3 identity matrix that has 1s on the main diagonal, 0s everywhere else. So we need to find out what this determinant is. So we'll expand along the first column. Determinant of A minus lambda I is going to be minus 1 to the 1 plus 1 times 3 minus lambda times the determinant of this submatrix. The next term is going to be minus 1 to the 2 plus 1 times 0 times something, so that's just 0. The next term is going to be minus 1 to the 3 plus 1, which is 1, times this 1, times the determinant of this submatrix up here. And so the determinant of A minus lambda I is equal to this. We just got two terms because one term was trivially equal to 0. Multiply this out, remembering the determinant here is 5 minus lambda times 3 minus lambda minus 10. Over here, this determinant is 10 minus 5 minus lambda, which we have here. Do the algebra, and we find out that the determinant of A minus lambda I is equal to this. Factor it, and we can factor a lambda minus 2 out of that times this other factor, minus lambda squared plus 9 lambda minus 10. And now set this equal to 0 and solve for lambda. lambda minus 2 equals 0 when lambda equals 2. This quadratic term, this factor here, equals 0 when lambda equals this number or lambda equals that number. They're the same, except here you have a minus, here you have a plus. We just use the quadratic formula by setting this factor equal to 0 and solving for lambda. So these are the values of lambda that make A minus lambda I not invertible. We'll find out in a later lesson that these values of lambda are called eigenvalues of the matrix A. So let's see how we can solve this equation using sage math. I'll have to use a different letter than the Greek letter lambda because lambda has a special meaning in Python and sage math. So I'll just use alphas here instead of lambdas. So the matrix that we're going to look at is this one, and we defined that matrix up here. We defined alpha to be a variable, then A was a matrix. The first row up here was 3 minus alpha, 2, and 1. The second row here is 0, 5 minus alpha, 5. The third row is 1, 2, and 3 minus alpha. So A will be the matrix with those 3 rows, and we'll show A. That will display the matrix A as the output. Here it is. Then let's factor the determinant of A. When we do that, we get minus the quantity A squared minus 9A plus 10 times the quantity, I should have said alpha, times the quantity alpha minus 2. When we solve that determinant is equal to 0, solve it for alpha, we get alpha equals 2 from this factor, and we get 2 more solutions. Alpha is 9/2 minus 1/2 the square root, and 9/2 plus 1/2 the square root as the other 2 solutions to this quadratic factor equals 0. We find the determinant, as we noticed up here, by using the name of the matrix dot det and parentheses. We can solve an equation in sage math by saying solve and then the equation, which in this case is this determinant equals 0, and we're solving it for the variable alpha. So now let's discuss Cramer's rule. Cramer's rule gives us formulas it involves determinants, to solve the equation ax equals b for any of the components of this vector x. Cramer's rule lets us solve for these components one by one. So if we're only interested in finding the value of x1, we can use Cramer's rule to do it. If you want to find the values of x1 and maybe x sub 3, then you can use this formula twice, once to solve for x1, another time to solve for x sub 3. The rule that we're about to look at, Cramer's rule, only works if A is invertible. And so let's see what Cramer's rule tells us. Let's let A be an n by n invertible matrix, and let's let A have these columns. The first column is A sub 1, second column A sub 2, all the way through the nth column is A sub n. So in general, A sub I is the ith column of A. Now let's let A sub I of B, notice this depends on an I and also a vector B, which is up here. Let's let that be the matrix obtained by replacing the ith column of A with B, this column vector. Then, if you want to find the value of x sub I, it's given by this formula. The determinant of this matrix that we just talked about, A sub I of B, divided by the coefficient matrix determinant the determinant of the coefficient matrix, determinant of A. And this formula holds for I equals 1, 2, 3, all the way out to n. This formula is basically Cramer's rule. So for reference, here's the formula for Cramer's rule. And let's look at this problem. Let's consider this system of equations. They're linear algebraic equations. And let's solve for x sub 1 and x sub 3. Okay, so x sub 1 then is going to be the following. First, let's look at the denominator here. This denominator is the determinant of the coefficient matrix for the system of equations. So the first row in this denominator is going to be 1, 2, 3, which we see right here. 1, 5, 1, which we see here. 3, 2, 1, which we have right here. Now, since we're solving for x sub 1, we're going to alter this matrix just a little bit to get this numerator. We're going to replace the first row of this matrix here with this b vector, column vector, which are the constants on the other side, 10, 20, and 30. Now, if we evaluate the determinant of this 3 by 3 matrix, we'll find out it's minus 280. If we evaluate the determinant of this denominator, it turns out to be minus 32. Minus 280 divided by minus 32 is a positive 8.75. Now, to find x sub 3, we're going to use the same denominator we had up here, so it's still minus 32. But since we're finding the third variable, this numerator is going to be very similar to this denominator, except we will replace this third column by 10, 20, 30 right here. So now, if we evaluate the determinant of this 3 by 3 matrix, it turns out to be 40. This determinant we already saw was minus 32, and so this, when you simplify it, is minus 1.25. Now, if you look at this, you may say, well, wait a minute. We could have solved for x1, x2, x3 all at once by using our formula x equals A inverse times B. So why didn't we use that instead? Well, I don't really have a very good reason for not using this. Both will work. But it might be that if we were using computer software, computing A inverse times B, at least for this 3 by 3 matrix, would be quite easy to do. And we could find the answer by just using matrix and vector operations, let's say perhaps in Sage Math. If we're doing this problem by hand, though, it might take you a while to find A inverse. If you look at what we did over here, we don't see the inverse of any matrix having to be computed. We're just taking the determinant of a 3 by 3, dividing by a determinant of another 3 by 3. So if you're doing this by hand and maybe punching in sums and products on a calculator, it might be easier to find the values of x sub 1 and x sub 3 this way than by inverting A by hand, maybe using Gaussian elimination. There's not really a savings in efficiency when it comes to using a computer by using Cramer's rule. A inverse B is, my guess, probably about as efficient as you can get if you find A inverse by using Gaussian elimination. So what did we accomplish in this lesson? We defined and calculated the determinant of a 2 by 2 matrix. We defined and calculated the determinants of larger square matrices using expansion by minors. We learned a few properties of determinants that would help us in the future. We saw that a square matrix A is invertible if and only if the determinant of A is not 0. And we saw that if the determinant of A is not 0, then the equation AX equals B has exactly one solution. And if the determinant of A equals 0, then the equation AX equals B has an infinite number of solutions or no solution at all. If the coefficient matrix A is invertible, the determinant of A, in other words, being non-zero, we also saw that we could apply Cramer's rule to find the solution of n linear algebraic equations in n unknowns variable by variable, using Cramer's rule to find one variable's value at a time. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.